Now, diagram. So after we understand that, then the remaining, pretty easy, very straightforward. Okay. Number of comparisons for the worst case. Now, let's go through the whole binary search, and we want to see what is the worst case. Best case, easy. Yeah. The first time, you get it. Yeah. The hard is the worst case. Yeah. We want to see the worst case. So here, I list table, chart, do a chart like this. Number of comparisons. The first comparison, how much we can reduce the problem size. Yes. So we choose median to do the comparison, and we can drop one subarray, 1/2 of the problem size. So the data size after comparison is reduced by 1/2 of the original problem size. Okay. Second time, now we do another comparison. For the remaining subarray, we do comparison number 2. You can see we drop another 1/2 of the remaining subarray. The problem size is reduced to 1/4 of the original array, and so on. Okay? So we keep doing the split like this. After k comparison, we reduce the problem size this much. Okay? The size is this big. Okay? All right. How do you know we reach the end? For the general discussion. So here, we don't know what is the n number. How large is the n number? We don't know that. But how do you estimate? At a certain point, we need to stop. We cannot do forever. We cannot split forever. We have to stop at some point. So how do you measure? How do you find the criteria that can tell us we should stop right here? Any idea?
When there's two values left in the array.
Two values. All right. Our array size is this much. Okay? He said this subarray contains at least 2 elements, right? If you have 2 elements, can we still do split? We can still do another split, right? So if the array size greater or equal to 2, we can still do another split. Here, I want to find the point. We cannot do split. We do not need to do split. We do not do split. Okay? Yeah. We should stop. Okay. Yeah. All right, so after last comparison, let's check if this array size already smaller or equal to 1. How about that? Right? Data size less than 1. How can you split? Right? You cannot split. Because if it's slightly more than 1, we may still, probably we can include 1. So, because for 1 you cannot split, right? Yeah. Less or equal to 1, then. So nobody even think about it doing split. Okay?
Could you set the n over 2k equal to 1 then?
Yeah. Equal, but because we don't know if they're equal or not. All right? Yeah. So that's why we need to use this inequality. Yeah. Okay. All right. So here, okay. This tells us. Okay. All right. K plus 1 comparison, right? Because this is the data size for the K plus 1 after K plus 1 comparison. That one still greater or equal to 1. Then after we do one more comparison, immediately below 1. Now we catch the point. We catch that point. Yeah. Okay. Yeah. You cannot do more, you cannot do less. We catch the right spot. Okay. So here we can estimate that K. That K, so we know that's the number of comparison for the worst case. That's the worst case. Okay? So that inequality, we use inequality. Okay? Yeah. All right, so we simplify it. Yeah? So common denominator, taking log, we get this. Taking log, we get that. Okay? Then we use floor ceiling function, right? Yeah, floor ceiling function. So, oh, sorry, yeah, some students still writing, yeah. All right, now, derive the worst case formula from the inequality. Okay. All right, floor ceiling function, yeah, right? Floor ceiling function, okay? Yeah. If we take floor function, we get k, right? But we need also another possibility, ceiling function from this side, we can estimate that. Yeah. Because there is an equal sign here, so it's better to take floor function first. Yeah, that will be easier, right? Yeah, so that's why this k integer, that log 2 not, but we can take floor function. Yeah, so take the floor function. Yeah. But for the worst case, right? Yeah, largest possible k, that's the worst case. Okay? Yeah. So the final formula for the worst case, k max, that's the worst case. Yeah. Maximum number of comparisons. We need this formula. See? 1 plus. Yeah. So I think we are pretty much familiar with this formula, right? Yeah. We did many exercise questions regarding that expression. Okay? Here, did you ever think about that formula we used many times? How does it, come from? Right? Have you think about that? So here, you will see from this inequality, you will see it. Right? All right, so let's see. For n equals 7, let's plug in. Yeah, 7, 2 point something, right? 2 point something. So floor function 2. 2 plus 1, that's 3. Yeah. That means for a 7-element array, the worst case, you only need to do 3 comparisons. You can, reduce to the last element. Okay? The last one. Yeah. Yeah. But when n equals 8, one more than that. Okay? One more. 8. 3 plus 1, 4. See? So if your array has 8 elements, power of 2, 8 elements, then one more than that. Okay? 1 element increase, 1 more comparison. Okay? Yeah.
Quick question. So in the beginning, when you start comparing, when you have like 1, 2, 3, 4, 5, 6, 7, and 8, like how do you pick between which one?
Oh, good. Yeah. So he's asking me, because we have even number of elements, which one is in the middle? How do we define the median, right? So here, that's the definition of median. All right, so good. That's a good question. So let me answer in this way. Okay. When we have even number of elements in an array, then we have 2 medians, left median, right median. Okay? So we call left median, right median. Okay? But we can only pick one. So we usually, most of the time, we pick left median. Yeah. Left median. Okay. All right. Yeah. Now, from this side, how do we represent it? n plus 1 log of base 2 ceiling function, because this is strictly less. Okay? If we just take ceiling function directly, it may not be equal. It could be still strictly less. Okay? So that's why we increase that by 1. Okay? Think about it. We increase that by 1. This number will increase by 1. So we increase that number by 1. Okay? Then ceiling function. Then it has a chance to be equal. Otherwise, still strictly less. Yeah. So that's why we increase that by 1. Okay? So in that expression, that's the formula we are familiar with. Yeah, that's the case. Yeah. So from this binary search, you can see that's how that formula comes from. Yeah. Okay. All right. Yeah. So we have this formula. Okay. All right. Yeah. So here you can see that case. Yeah. Right. So here another view to look at that. Yeah. Another view. Right. Because we know n is in that range, right? This side less than, strictly less than. Okay. If we reduce it by 1, we can make it equal, right? Yeah, because this is strictly less than. That contains equal. This side, no equal. But how do we tight? Yeah, because this is still a little loose. How do we tighten it a little more? We tighten, okay? Tighten the inequality a little more. Reduce this number by 1, so we make it tight. Okay? Now, this side could be equal. Both sides could be equal. So then, when we take log floor ceiling function, we will get that. We will get that. Right? Because this time it contains the equal sign. Then it's safe. This time, no equal sign. If we do the ceiling function, we are not sure if we should take equal or not. Okay? It's not guaranteed. Yeah. But when we have this equal, when we do floor ceiling function, now we know we can get it. Yeah. All right, so that's the reason we have this formula. Okay. All right, so that's the worst case. Yeah. So you can see, much harder than before. Yeah. Next, another case probably even harder than this. Average case. Average case. Okay? Now this is a good example for average case. How do we calculate it? How many comparisons do we need for average case? Right? So, yeah. Let's see. The next slide. Let's look at the average case. Right? All right. Average case efficiency. Best case we know it's 1. The worst case we know that number. But what is the average case? Okay. After we learn so many examples, I hope you never do the average of those two numbers, right? Never do that. Yeah. At least you should think about. Yeah. Do not quickly make your answer. Yeah. So here the answer is wrong. If you do that, it's wrong. Yeah. Why? So let me explain. Yeah. Let me draw a simple example to show you why it is wrong. Okay? Yeah. We use an array of 7 element array. Right. So let's look at, because we can do experiment. We can do experiment on 7 element array. How many comparisons do we need by average? We should consider all the possible cases. Then we take average. Yeah. So That's the definition of the average. Yeah. So let's do it in this slide. 7-element sorted array. So that's our data. Yeah. So I draw a diagram like this. Sorted. Okay. Yeah. That is our key. So binary search. Okay. All right. We need an assumption. This V is in the array. Yeah. Then, we can get a clear answer. Otherwise, we need to look at the probability, right? Yeah. There is a probability issue. Yeah. But now, so we want to avoid that probability issue, so we make this assumption in the array. So don't worry about the probability. Okay? All right. Now, the first comparison. There is one case. If the V equals element number 4, we need one comparison, right? Yeah. So that's the first case. Okay. After that, we draw a binary tree. This is a binary tree. Yeah, because the next left subarray, right subarray, for the left subarray, we need to compare V with element number 2. For the right subarray, we need to compare V with element number 6. Okay? That's why we draw 2 child nodes like this. Okay? So these 2 elements correspond to 2 comparisons. If V equals any of the 2, we need to use 2 comparisons. So that's why we draw like that. Okay? Going down, the remaining 4 at the same level like this, we need to make 3 comparisons. See? Yeah, we get a nice tree, binary tree. Okay? This is we call a complete binary tree. Complete. Okay? Yeah, perfect binary tree. Okay? Now, look at this diagram. How do you calculate the average case efficiency? Do the average, yeah.
Count all the comparisons and divide by 7.
Right. We have 7 cases. You need to add up the comparisons for all 7 cases, then divide it by 7. Okay? What is the total number of comparisons for all 7 cases? Then divided by 7. Right? Yeah. So 1 comparison case, you only have 1. So 1 times 1. 2 comparison cases, you have 2. So 2 times 2. Okay? 3 comparisons cases, you have 4. So 4 times 3. Then you take weighted average. Weighted average, so you get this 17/7. That's how you take the average. How about that? That's the way you take average. Okay? Yeah. All right. Yeah. Think about if I give you a number not power of 2 minus 1. So here the number I give you, it's the best number, power of 2 minus 1. So you can draw a complete binary tree. But I can give you an arbitrary number. For example, I give you 100. N equals 100. Binary search. Okay? I ask you calculate what is the average number of comparisons do you need to do the binary search. Okay? You need to, based on the binary search, right? When you have even, you use left median. Okay? Use that rule, left median. Every time when you have even elements, left median. Okay? Can you draw a binary tree? After you draw that binary tree, can you calculate this weighted average? You count the number of 1 comparison, how many? 2 comparisons, how many? And so on. Okay? Then you take average. Yeah. Okay? All right. So, by the way, at this point, This weekend, I will post our exercise number 3. Okay? Yeah. So we practice these questions. Okay. Next week, before the spring break, I will post our homework assignment number 2. Okay? Yeah. All right. Yeah. Another possibility. Sometimes I may assume the probability is P, right? Yeah. Not 100%. I give you, P, 70%, right? So then I ask you some question. Okay? Yeah. Also think about that. Using the linear search, we did that. P, right? The probability. So we have that formula, right? So here, binary search, we can have the same thing. Okay? So you will see either in this exercise set number 3 or homework assignment number 2. You will see those similar questions. So I want to practice if you know how to calculate. Okay? All right.